Hi, in this video, I'm going to review Lab 3, the lab where we investigated the projectile motion of a ball on the slope. Okay, so you have set up the experiment and the first thing you were asked to do is actually to measure and record the angle of elevation of the board from the horizontal. So most of you actually use a protractor. However, when you're actually measuring using the protractor, you find that actually the baseline of this protractor is not touching the base, so it's actually a little difficult to measure the angle. So one way you can actually help yourself is to actually use the spirit level or something that's horizontal and place the protractor that's on it. Okay, and if you look at it, you will find that the angle of the elevation is also actually given by this angle here. Okay, so that's one way you can position it. Alright, then the other way you can position it is actually like this, where we actually measure the angle of the top slope instead rather than the bottom slope. So this is how you can actually use the protractor, especially if you did not set up your setup close to the edge of the table. Okay, so you don't always actually have to measure it from the base here. Okay, as long as the angle is the same. Alright, so for this one, the key marking point in the recording would be that this is a raw reading. Hence, we would need to record to the smallest division of the instrument. In this case, it is a protractor, so we are actually recording to the nearest degree. Okay, this is another method to measure the angle of elevation. So some of you actually use, instead of using the protractor, you use the ruler. So in this method, they actually measured the height of the ramp and the base of the ramp using a ruler. Then using trigo equations, they compute the value of alpha. So it's an acceptable method. In this case, your raw readings would be the value of y and x. Since they're measured with the ruler, then they should be recorded to the nearest millimeter. Alpha itself therefore becomes a derived reading, and since it's in terms of tangent inverse, these two values, hence it follows the least SF of the raw values. So this is 3SF and this is 3SF. So the value of alpha should be given to 3 or 4 SF. There's no need to increase one more because I think 19.1 is good enough. So this is another method to actually measure the value of alpha. Once you've done that, you're asked to launch the ball bearing. After you ink the ball bearing, you are supposed to launch the ball bearing on the ramp, and then from the tracks measure the maximum range, horizontal range, and maximum height reach. Now, after you have done one experiment, you will find that actually, even if you want to repeat it at the same theta at 15 degrees, you'll find that the tracks don't actually match up each other. So in this case, this is a case whereby it would make sense for the values, for the experiment to be repeated and two sets of readings to be taken. So once you've done that, this is the way to record. I will have two sets of values and then I would find the average. Now the raw readings are again measured to the nearest millimeter because they're measured using a ruler. So that would be one of the marking points. Now x max and y max itself become derived readings, but if you look at the equation, it's based on x max 1 plus x max 2 divided by 2. Now 2 is an exact number, so x max depends only on these two values. So these two are addition, alright, so we'll follow the dp. So hence this is 1 decimal place, this is 1 decimal place. So logically, x max should be recorded, the average should be recorded to 1 decimal place. So it follows the same for y max as well. Then once you've completed the first set of experiments, often the first set of experiments is for you to check the accuracy of your data, or for the examiners to check the accuracy of your data. Alright, but in this case, we're not marking it here today because our alpha are all different. Okay, but then you're asked to repeat part C for different values of theta. Now, before you go on, you should actually read through the whole experiment. You know that eventually you're going to need to plot some graph. So before you repeat the different values of theta and actually record your x max and y max for different values of theta, we need to plan out our table because only one table is allowed. Alright? Therefore, you actually need to skip to part E and plan and think of what is the eventual graph you're going to plot. So you're given this equation, y max equals to u squared sine squared theta over 2g sine alpha. Okay, so what graph am I going to plot here? Now, first identify your independent variable. So my independent variable in this case is actually my theta, and my dependent variable is actually my y max. Okay, and then so the next thing would be do is to linearize this equation. Now this equation is actually linearized nicely for me, but I may just want to rewrite it out so that my constants are clear, my variables are clear. So once you linearize the equation, you will find that it can be linearized to the form of y equals to u squared over 2g sine alpha. All these here are constants in my experiment, and then times sine squared theta. So this is of the form of y equals to mx plus c, okay, where c is actually 0. Alright, okay, so with that linearized, I can now actually state my linearization statement. So this is actually the linearization statement. Now in your linearization statement, there should be 3 parts to the statement. Number 1, alright, what is the graph you're going to plot? Number 2, what is the shape you are going to obtain? And then how are the constants related to your graph? Okay, so this would be the 3rd part. Alright, okay, so it would sound something like this. Please write them out properly. I'm going to plot the graph of y max versus sine squared theta. Okay, and because it's linearized, I should expect a straight line graph. The gradient of the straight line graph would then be u squared over 2g sine alpha, and the vertical intercept should be 0. Now you note that, I did note that quite a lot of you, because you wanted to look for u squared over g, you decided to plot sine squared theta over 2 sine alpha. Now that's allowed, but it's not actually recommended, because there will be quite a lot of computation to actually add in compared to sine squared theta, and there's actually a greater tendency to make mistakes. And once you make careless mistakes in computation, then what's going to happen is your graphs may come out to be weird, and you're going to be disturbed by it, and you may not be able to draw your best fit line properly. So generally, we try to keep our y values and x values very clean of the constants if possible. And then we will treat the constants separately when we are processing the gradient. Okay, so that's a recommendation. Once you've planned out what you want to plot, you can now plan your table. So you are expected to give only a single table. You will be penalized in exams if you give us split tables, because it reflects that you didn't plan your experiment carefully. So before you plan the table, you may actually want to count the number of columns that you want. So I'm going to have 1 column for denoting the number of data sets. Okay, I'm going to have theta. My raw values would require theta since I need sine squared theta. I'm going to repeat my experiment. So I'm going to have an x max 1, x max 2. Then I'm going to have a y max 1, y max 2. The question asks me to determine x max, so I'm going to have x max, and the question, I'm going to plot y max, so I'm going to need y max for 1 column, and finally I will need a sine squared theta. So counting, I would have 1, 2, 3, 4, 5, 6, 7, 8, 9. Now once you know that you need 9 columns, you can plan the space better, you can go and draw your columns. Now the other trick that you may want to do is, you may want to start your columns at the edge of your question paper. Okay, then leave some space behind in the case you forgot and you really need to add additional columns behind. Right? Similarly, for the rows, we know that you only need to take 6 sets of readings. However, in the case that you need to add additional, you may therefore not want to close off your table and then not plan out such that your table is all the way to the edge and you have no more space in the case that you need to add in additional rows. Okay, now beyond the table, for the derived readings, you need to tell us how do you get these values from the raw readings. So you should state for us, like define what is x max, okay? It's derived from x max 1 and x max 2 divided by 2. Similarly for y max, okay? In my processing of data later, I'm going to need alpha. Now, alpha is a constant that remains the same throughout the whole experiment. So you don't put it into the table, but you actually leave it outside. So alpha should be recorded at the top of the table as well. With all that planned out, you can do your data, collect all your data and record them down. Now, it is not recommended that you record in pencil. It's recommended you record in pen because time will be very tight in exams. So try and get used to collecting the data and immediately recording it in pen. So plan your table before you start your experiment. Okay? So once you've done that, and you record all your readings. Now, in terms of the table, this is what we're marking for. First, again, convention for the column headings. All your column headings should have a quantity and units, and the convention would be quantity / units. Now, take special note of sine squared theta. Sine squared theta is actually a dimensionless quantity. However, because theta can be measured either in radians or in degrees, so often we want to tell the examiner that we've recorded in degrees. This is the convention. So degrees belongs to the theta, then we bracket the whole thing, then we put our sine squared outside, and so the whole thing is dimensionless. And again, equations and constants for neatness sake should be placed outside the table. Okay, now the next thing we want to, once you've recorded everything, the next thing we want to mark for is whether you have recorded your raw readings in the correct manner. So the thing we are looking for is whether it's recorded to the correct DP. So again, the rule to follow is to follow the smallest division of the instrument. Theta is measured in degrees, so and using a protractor which has 1 degree, the smallest division, so theta should be measured to the nearest degree, recorded to the nearest degree. All the x values and all the raw readings for the y values were measured using the ruler, so all the y and x values should be recorded to the nearest millimeter. The next thing would be your derived readings, and here we are checking whether the DP is correct or whether the SF is correct. Okay, so 2 rules we'll need here. We note that x max and y max, like earlier on, is made up of the addition of 2 raw readings divided by 2, which is an exact number. So we follow the addition and subtraction rule, and it should follow the least DP or one more. But in this case, because we have a good spread of values, so I think following the least DP would be good enough. So these are all to the nearest millimeter. So your x max and y max should be recorded to the nearest millimeter. Now for sine squared, it doesn't fall into addition and subtraction. It follows from trigonometry. So if you check your practical booklet, then what we will look at is we are looking at the SF of the raw values. So the raw value we are looking at is theta. So theta were all measured to 2SF, so I'm recording all to 2SF. Do you want to record one more than the least? Will depend again on the spread of values. I've got a good spread of values from 0.9 all the way 0.06, so I think that will give me a good spread on the graph paper, so there's really no need for me to record one more than the least, so I'm going to keep to the least. But please be consistent when you apply your rules. Please don't mix that and have some of them following the least and some of them having one more than the least, especially within a column. Okay, all right. Other reminders. Now, in exams, all your pencil work is considered as rough work. For this round, if you have done your work, you have done your recordings in pencil, I did not mark. Okay, it's just to remind you that all these are rough work, and so I did not mark, I did not grade, I did not give any feedback. Please remember to therefore write in pen. Okay, the only exception is in graph, whereby all the work in graph should be done in pencil. So the next thing we're going to go through is your graph. Once you've finished getting your data, you've processed all your data, the next thing you would want to do is actually plan your scale. All right, and plan your scale is such a way that all your points should be able to fit into the graph paper. So The first thing we're going to mark for is axis. So you should draw your axis and then label them with the units. There is no need for title, there's no need for scale. So all you have to do is give me what graph you're plotting with what graph in this manner. But all your axis labels should come with units. Then your axis should be labeled with numerical labels at 2 cm intervals, and the tick marks must be clearly drawn. So what do I mean by tick marks? Now these are tick marks. So please make sure you actually do put in your tick marks, alright, and please draw your axis with proper ruler. Next would be the scale that we are marking for. Your data points must occupy more than half the graph paper. This means from your first point to your last point, it should occupy more than half horizontally and more than half vertically. Today we are using the normal graph paper, so usually you should actually count your graph paper. In this case, your normal graph paper has 12 squares, 12 big squares in this direction, and in the shorter end has 10 small squares. This is why, since I've orientated my graph paper in a landscape mode, all my points should encompass more than 5 boxes vertically and more than 6 boxes horizontally. Then the next thing I'll check for is whether the scale is odd. So nice scales are 1:1, 1:2, 1:5. And if you really don't have a choice, you can use 2.5 or 1:4. But 3, 6, 9 are definitely out. Now this time round, I've got very, very odd scaling, as in the scale is 1:5, but I have people who give me 7, 12, 17, 22. This is not the conventional way we label a scale for a 1:5 scale. So that is also considered odd scale. So please take note of that. What you would do is put in the plots. The next thing we would count is if you have taken 7 plots, you should have 7 data plots down here. And all the data plots in the table must lie within the grid lines of the graph paper. I do have people not planning their scale carefully, and then you plotted one point outside. That point reflects that your scale is bad and is not counted as a plot that is plotted. Okay, so it must lie within the grids. And then all the plots must be plotted to the accuracy of half square. During day-to-day practice, we do not usually check, but in exams, please be assured we will definitely check whether you have plotted correctly. Markers wise, most of you were able to use conventional markers like crosses like this, and most of you have reduced the size of your markers to make it the size of the smallest square. Okay, so that should be quite fine. The next marking point would be the best fit line. So it should show again even scatter on both sides, not just simply by the number. So you can have, for example, 3 there and 2 here. Alright, but more importantly, please balance the distances. And if you can't, you may also want to check the rotation of your straight line graph a little bit to check whether it can give you a better fit. Alright, now there were also quite a few of you which started your graph from 0, 0 because you expected the graph to pass through 0. However, in any experiment, we will always possibly have some random errors. So even though the theoretical value is 0, you are not expected to actually pivot your graph at 0, 0. So you should plot based on this trend. In the case that there is some deliberate systematic error that's introduced by the examiner. Alright, so just take note of that. Okay, what do you do if anomalous points are present? Some of you actually just say circle it. You didn't actually write anomalous. So if you have one point that's extremely off and you find it very difficult to put into the graph, then you should not only just circle it, but please label anomaly or anomalous. Alright, and you should do that before you draw your best fit line. The best fit line should be drawn after you circle it and ignoring the anomalous point. The next thing would be finding the gradient. Once you have done all this, you would draw the gradient triangle. Please note that your gradient triangle should be drawn in dashed line because it is not the best fit line. You don't want to confuse the examiner. Alright? And the gradient triangle must be drawn in such a way that the hypotenuse of the gradient triangle must be greater than half the best fit line. So what you would have is, this is the hypotenuse, and it must be greater than the length of the best fit line drawn. Okay? Try to choose nice intersections so that's easy for you to read. And when you take the read-offs, it should be read off to a half square accuracy. And because you're reading the x values from the same x scale and the y values from the same y scale, you should therefore be consistent in the way you report all your x values and all the y values. Okay, and the way to present your gradient working would be like this: the gradient triangle and the coordinates labeled clearly. There's no need to label this corner here because you're not going to use it. Okay, and please don't just draw arrow and then label the value here. No other working should be done for gradient on the graph paper. Then we will go back to our paper and we will now go and compute the gradient using y1 minus y2 over x1 minus x2. Please transfer the values as they are together with the decimal place so that you don't end up reporting too few decimal places. So once you do that, you compute, you should get a value. Alright, now you notice that I've put in units here for my gradient. There is no units for gradient mathematically, but however, because my gradient has a physical significance, and I'm going to use my gradient later to compute u squared over g, and I didn't work in SI unit. So for good habits, usually if I'm not working in SI units, I will put in the unit for gradient. So this is a y value, a y max value, so the unit is in cm, and then this is a sine squared theta value, so there is no units for this. So my gradient has a unit of cm, and this will help me later when I'm computing my u squared over g to find the units for u squared over g. Alright, again logically, because these two are read off from all the from the y-axis, so these two should have the same decimal places. Similarly, this is read off from the x-axis, so the denominators must also have the same decimal places. Alright, so this is one obvious point. If it's not the same, I can actually deduct marks in exam. Alright, and a lot of you just scribble numbers without writing statements. Please remember, this is a presentation where you are trying to talk to the marker, and you are trying to tell the marker how did you actually carry out or find these values. So please present your working properly in a logical manner to the marker, so you can actually use this as a guide. Then the next part of the experiment, we actually want to determine u. But before that, we actually need a value of g. So you're asked to do a second experiment whereby you are asked to find g, and then you are dropping the ball bearing along the slope from a certain height, 5 cm, from the top edge of the mahjong paper. Alright, now when you release the ball, you will notice and start timing and stop timing, you will realize that the timing to fall that particular distance is actually very short, less than a second in most cases, and therefore it would make sense, because human reaction time seems to be very significant here, to take repeated readings of this timing. Now it will look very suspicious if you have 7 timings and all 7 timings look exactly the same. Okay, and anyway, please don't go and take 7 timings in exam. You do have limited time in exams, so please don't spend your time working up taking 7 readings, because it's not going to give you extra credit. But in the end, because you went to take 7 readings, you may end up not finishing the paper. Alright, so the minimum is 2. I'm going to keep to two values. Again, recording, all raw readings should be recorded. S is measured with a ruler, so it should be recorded to the nearest millimeter. T is recorded with the stopwatch. My smallest division of the stopwatch is 0.01 seconds. I'm going to record the value as displayed in the stopwatch here. So this is what we do usually when we record the value of t. We just follow the stopwatch. But inherently, if you're asked to do some uncertainty for timing later, you know that there will be a reaction time of 0.2 seconds. That is the place where you can actually truncate your decimal places. Alright, and so this would be the way to present your data. Then with these values, you are asked to compute a value of g. So most of you were able to tell me that s is equals to ut and half at squared. This is the equation you're going to use. However, quite a lot of you forgot that your ball is actually rolling on an inclined plane. So the acceleration is not g, but g sine alpha. That's why you needed the value of alpha earlier as well. So with that, your initial velocity is 0. That simplifies to half t squared g sine alpha. And making g the subject of the formula, it will be 2s over t squared sine alpha. Then you can substitute everything inside and then compute the value to get around 8.66 or 7 point something, somewhere around that value. Okay, the orders of magnitude should be correct. So mark is awarded for clear working to show how g is computed, not just suddenly miraculously having a scramble of values. So clear working means that you tell me what is the equation you use and what are the values you substituted. G must be computed correctly, and therefore there should be correct SF for G. So most of my values here are 2 or 3 SF. Because G is an intermediate value I'm going to use later for computing U, so I've taken one more than the least and I've decided that to keep it in 3SF instead. Alright, and then finally also be that reporting a correct unit for G that is coherent with the value. So again, this is a case whereby if you have put units into your working, then it will look a lot more sensible and you'll be a lot more careful in the conversion. Finally, we want to determine the initial launch speed of the ball U. So earlier on, we've got U squared over G equals to 13.9 cm. So that leaves us that U is equals to square root of 13.9 times G. So put in the two values you found calculated earlier. And since you know this is in cm and G is in meter per second squared, so you would need to convert your value of 13.9 cm into meters, and then that will give you a value around this value. So clear working to show how U is computed from the earlier parts. U computed correctly, correct SF for U, and correct units for U. So the last part of the experiment, you're asked to comment on how reasonable the value of U is. So this part of the answer is actually to get you to think about whether your value of U is reasonable, and sometimes it's a hint to you to check whether you have converted your units correctly. So examples of how you can comment on how reasonable the value of U would be these two. For example, you can use it to look at something that compare it with something that you're familiar with. For example, maybe the speed of a car going at very low velocity at 20 km per hour. So since what you got is meter per second, you can do a quick conversion and convert it into kilometer per hour, and that is about 4 km per hour. And you see that this is only 1/5 that of the speed of the car, and hence this is a reasonable value. The other way is if you have looked at other values earlier, you can try and see if there's any hints in the earlier part of the experiment that may suggest whether this value is reasonable. So for example, in part F of the experiment, we saw that in about 0.8 seconds, so that in part F in about 0.8 seconds, the ball traveled actually about 0.65 meter down the slope. So comparing the two values, they seem to be very close. Therefore, it would seem that 1.10 meter per second, which is slightly larger, okay, and still comparable around the same order, is a reasonable value. So this is how you can actually comment on how reasonable the value of U is. I did note that some of you left this blank. For exams, try not to leave blanks. Write something. You never know. Sometimes you will be able to get some marks for some comments. Okay? So that ends it for the review.